All right. So this is lecture 10, and we're going to make an effort to finish everything about the 4 fundamental subspaces. The only thing that is going to be missing and will be discussed starting maybe on Friday if we finish today will be to discuss the orthogonality of some of the subspaces. Why 2 of the subspaces, for example, they can make the whole of Rn or the whole of Rm. That's a very important problem. But today we will finish with clarifying everything about, you need to know about the dimension of the subspaces, how to find the basis, everything that it was in homework 1, and everything that's going to be in homework 2, because homework 2 is really a repeat of homework 1 with more problems. I decided not to give you anything new in homework 2. Okay. So let's keep moving. There is lots of things to do. So we have to discuss about the dimensions of the 4 fundamental spaces. Literally today will be sort of the fundamental theorem of linear algebra. The whole of linear algebra is actually this lecture today. Okay? So, so let me put a few statements that we already have seen. So the column space and the row space both have dimension R. All right? We discuss about this, you know, and we will reiterate today. And that R, we call it the rank of the matrix A. The null space has dimension n minus R. You remember n minus R, or the number of the free variables. And those numbers of free variables defines basically a basis for the null space. So it has dimension n minus R. Now, today we're going to define another new space, which is going to be the left null space. All right, it's going to come up. And the left null space is going to come back to have dimensionality m minus R. So we will see what this left null space is. Sounds weird, left null space. The other one doesn't say right. You know, it's just, we could have called it right null space, but we call simply the null space. So all the information, hopefully you have realized this by working on the homework, all the information regarding these 4 fundamental spaces is contained on this matrix R. Everything is there, all right? And so we will see this again today. Something that I emailed you yesterday, and we will try to discuss it once more today, is when you do elimination, elimination is combinations of rows. So effectively, the row space doesn't change, but the column space changes. So the column space of R is not the same as the column space of A. This is a very key thing. The column space of R is not the same as the column space of A. What is the same is, you know, the number of columns that they are independent in R, the corresponding columns in A, they're also independent. So you have to look back on A to extract what the basis of the column space is. Correct? So you don't, you know, so we will clarify this with one more example today. And then we will talk about the wonderful decomposition of matrices in some of rank 1 matrices. And I know somewhere, maybe in lecture 4, I had discussed this with some examples, and I told you this is very, very important, and we're going to come back to it. So today will be one of those lectures, and there will be many more where we write things as summation of rank 1 matrices. I know you forgot what rank 1 is, so hopefully we will have time to remind you today. Okay, so let me put all of these things up. So we have 4 fundamental spaces. I'm going to start with the easy ones. The column space we denote as C of A, and it is a subspace of Rm. If you think of a matrix M by N, right? The column space is the space basically you generate by taking linear interpolation of the columns, linear combinations, I'm sorry, of the columns. And obviously the columns are in Rm, so C of A is a subspace of Rm. The null space is the solutions of Ax equals 0, and it is a subspace of Rn. Right? A is m by n times x, so the dimensionality of x is n, so it is a subspace of Rn. The row space, the notation we use, the row space is basically the space generated by taking the span of the rows. And the rows are of dimension n, right? And we denote the row space as C of A transpose. Why is that? Because the row space is the same as the column space of which matrix? In the row space, we look at the rows, right? So if you take those rows and you make them columns, what is the matrix you get? A transpose. So the row space the same as the column space of A transpose, and the notation we will be using is as the column space of A transpose. So we're referring to the rows, but that's the notation used in the literature, and that's what you need to use. And then, of course, we will discuss about the null space of A transpose. And for now, you can affiliate the null space of A transpose is nothing else, is the vectors y such that A transpose y equal to 0. Right? That's what null space means. But it's the null space of A transpose. And it is because A is m by n, right? This is n by m. So the null space, the left null space is a subspace of Rm. All right. So since we haven't spent much time with talking at all about the left null space, so let me discuss a little bit about the left null space. So this is our definition. The vectors y such that A transpose y equal to 0, they form the left null space. Okay? And so it is the null space of A transpose. But often what we do is to do the calculations and also to justify why we call this a left null space. If you take the transpose of this equation, do you agree with me? You can write it as y transpose A equal to the 0 row vector. Is that okay? Can you see now why I call this the left null space? Because the vector y multiplies the matrix from where? From what side of the matrix? From where? From the left. You have to keep talking today because if you don't talk, I'm going to give you all of this to read them on your own, and I'm going to say I'm done with the lecture today. Okay? So A transpose y is the same as y transpose A equal to 0, and 0 transpose, really. This is a column vector, this is a row vector. And remind me, when you multiply a matrix from the left with a row vector, what do you get in words? We spent a whole lecture on this, and I take you another video on this. When you multiply a matrix from the left with a row vector, what do you get? We said when you multiply A with X on the right, you get a combination of columns. When you multiply a row vector from the left, what do you get? Combination of rows. Thank you. So effectively, what we're looking is, we're looking to identify the combination of rows that gives us 0. Basically, we're trying to identify which rows depend on what and eliminate that. That's what we call the left null space. The same thing in the column space, we're looking what columns are independent, right? And those that they were depending on others, they gave us these free vectors, all right, these free variables, and the solution to the null space. Here, when we do this for the rows, we are actually getting a combination of the rows that are equal to 0, and this is what the left null space is all about. I am going to give you an extremely trivial way to identify the solutions to this problem using the information we already know. All right, so hold on. There is a slide, only one slide, that will tell you how to solve this problem right away by using the information from the R matrix. Okay. So this theorem, the fundamental theorem of linear algebra, has two parts. So in part one, discusses basically about the dimensionality of the spaces, and the dimensionality of the null space of A is n minus R. Even though I haven't done any computations here, the dimensionality, actually, can you see now, you remember how many independent rows I have in the matrix? What's the variable that defines the independent rows? How many? Which is the same as the number of independent columns, is R. So obviously, don't you think that the left null space, the number of dependent rows will be m minus R? right? If I have a total of m rows, R of them are independent, the rest have to be dependent. So the dimensionality of the left null space is m minus R. You need to know this up and down, left and right, okay? If you have to look, think, read, copy, it's not going to help us. N minus R, M minus R for the left null space. So in the part 2 of the fundamental theorem, we will actually discuss how these null spaces come together to form the whole of the space Rn and the whole of the space Rm. So this we have to wait until the lecture on Friday and next Monday, most probably. Okay. So let me start with one example. So we have, I don't give you what the matrix A is. For now, we don't really care. We have a matrix that is 3 by 5, okay? And somehow we do these row operations, and we get an R matrix that looks like that. So immediately, can you tell me what the rank of this matrix is? It says there, y it's equal to 2. 2 pivots, okay? And remember, the way we define the R matrix, the pivots, I bring immediately up in the picture the identity matrix that is R by R. The 2 pivot columns don't have to be next to each other, right? One is here, one is there. So in our case, the pivot columns is column 1 and column 4, but you can see 1, 0, and 0, 1, okay? So immediately, the pivot columns tells you that I have 2 independent columns, okay? Everything else is actually, all the other columns are combinations of these pivot columns. And you can see, if you take the second column, it's 3 times the first column. If you take this, the third is 5 times the first column. If you take 7, 2, 0, it's really 7 times this column and 2 times the fourth column, right? So just looking at the R matrix only at this time. All right, so we have R equal to 2, okay? So we need to discuss about the row space. What's the dimensionality of the row space here? How many independent rows we have? 2, all right? And immediately this comes up in the R matrix because you can see the zeros have achieved eliminating completely the rows that are combinations of the previous rows, right? And we always put the zeros on the bottom. So it is possible when you have this R matrix that somehow you did some row exchanges. All right, it is possible that you did some row exchanges, but effectively the idea here is if a row it's a combination of previous rows, it doesn't add anything to that matrix, so get rid of it, and we get rid of it with the elimination process, having those zeros there. Okay, so now, will you agree basically that the first 2 rows form the basis of the row space? Can somebody give me an argument just looking at the first 2 rows and convince me that they're independent of each other, all right? And as such, basically, you know, they span the row space, which we denote C of R transpose. Can somebody tell me, looking at these 2 rows, I mean, we already stated hundreds of times, but looking at them once more, can you tell me why the 2 rows are independent of each other? So I can understand too. Look at how they look. What is there that looks at you and says, we are independent? Well, but the linear combinations, they don't look at me. I want something that looks at me and says, look at me, I'm here. What is that? You remember 2 vectors are linear independent if you take any combination equal to 0. The only way you can have that is if the coefficients are 0. So what force is that looks at you and says, I'm here? I am going to be sure always when I take combinations of the first 2 rows, I always get 0 coefficients. What is there? Take combinations of the first row and the second. What part looks at you that enforces immediately these 2 rows to be independent? The pivots. which are 1, all right? You notice here, you have, if you take combinations, right, you're going to have C1 times 1. There is nothing below, all right? And that element will be the first element of the combination. It has to be equal to 0. The only way it can be 0 is if C1 is equal to 0. And if similarly I take, C1 and C2 combinations, when you look at the fourth element, because of that pivot 1, all right, and the other element being 0, I'm going to have C2 equal to 0. So the fact that you have that identity matrix there is what forces these two rows to be independent. Clear? Is the identity matrix that we managed to create by doing this elimination process that forces these two rows to be independent. So it's not a miracle. We don't just say they're independent. Just by definition of independence and having that identity matrix embedded there for the column rows and columns, and I'm sorry, and pivot rows and pivot columns, right? That identity matrix is what makes the two rows to be independent. All right, so the rank of the row space is equal to 2. The dimensionality is equal to 2, sorry. A subspace doesn't have a rank, right? Rank is only for matrices. So this, the row space has dimensionality equal to 2, okay? And we're still talking about the row space of R, okay? All right, this statement is what I just discussed with you. I put it in blue this morning, so when you read it, you cannot miss it, okay? Nothing new here. All right, so let me, since I see there is nothing else on the row space of R, if I ask you to find, so these two vectors that you see here, the two rows, they form actually the basis of the matrix R. All right, so this is basically the row space of R. If I ask you to give me a basis, you're going to say to me, it's a combination of 1, 3, 5, 0, 7 and 0, 0, 0, 1, 2. So what is the basis of the row space of A? What will be your answer? Say it again. The same thing. Why? Because these linear combinations were of rows, not of columns, so that hasn't changed. So if you want to have the linear, if you want to have this, the basis of the row space of A, you look at R, you find the independent rows of R, that's the basis for the row space of A. End of story. But, if I ask you something, you have to say with confidence, the basis vectors of the row space of A is equal to that. All right? Because you are not going to tell me the same thing about the column space. Okay, column space. All right? So similarly, you can see we have two independent columns. And again, it has to do with the identity matrix there, right? So there's two pivot columns. And so the dimensionality of the column space is equal to 2. So if somebody tells you what is the basis of the column space, what are you going to say for R now? What is the basis of the column space of R? Looking at that matrix, right? So what is the basis for the column space of R? We're looking at the columns, okay? So 1, 0, 0 and 0, 1, 0, you said? Yeah, that's it. Okay? So, but that's the column space of R. So if you want the column space of A, and that's really of interest here, you cannot take 1, 0, 0, 0, 1, 0 as the column space of A, because these row manipulations that we did in the elimination process have affected the columns, okay? What has not changed is the fact that the first column and the fourth column are independent because they are pivot columns. So if you want to compute, if you want to write down the two independent columns of A, the basis, let's say, of the column space of A, what are you going to do in this example? You're going to take the first and the fourth column of which matrix? Of A. End of story. okay? And if you say, no, sorry, I forgot, I wrote down the columns of R, well, you forgot it, but it's day and night, and if it's day and night, you're wrong. So here we have to take the first and the fourth column of A, not of R, of A. Okay. And again, all of this about the independence of these columns has to do with the beauty of the elimination process, where we brought up this identity matrix, right? This is what makes those two columns independent. Can everybody see, right? You can take any combinations of this, because you have here 1, 0, and here you have 0, 1, all right? Immediately you will find that these two columns are independent. Okay? I mean, take C1 times 1, 0, 0, and C2 times 0, 1, 0. The only way you can get this to happen is C1 equal to C2 equal to 0. Okay, so, the question then is, and already I put it up, maybe I should get rid of this. These pivot columns, they tell us the basis basically of the column space of A, and in principle of R, and in principle of A, as we just discussed. How about the other columns? Based on your homework, what does 300 and 500 and 720 tell you? Based on your homework. The rest of the columns, do we need them or they are useless? What are they? Where did you use in your homework the rest of the columns? Because if you did not use, means you did a lot of algebra that it was not necessary. Did you use the rest of the columns to do anything in your homework problems? For the null space. So these other numbers there, you know what they tell you? They tell you what combinations of the pivot columns you have to take to derive these other columns. So look at the column 300. It is obviously 3 times the pivot column 100, isn't it? Look at this column, 500. Don't you think it is 5 times column 1? And look at this. Don't you think it is 7 times column 1 and 2 times column 4? Can you see that? So they tell you the other columns depend on the 2 pivot columns, and the numbers tell you what combinations you have to take to generate these 3 columns. And obviously, if you reverse the signs of this and you set the free variables 1 at a time equal to 1, right, and the rest to 0, then you have the solution to the null space problem because of what we just described. All right? No miracles here. Linear algebra never lies. It's perfect. All right? There's no other subject of mathematics that is so clean. I mean, calculus is very clean, but you know, here, no ambiguity of anything. Okay? All right. So, for example, I give you here the dependencies between the different columns and how these numbers have to change sign to get the solutions, basically, to the null space problem. So we have done that already. All right, so we discussed about the column space. So I keep going and going. And these are the spatial vectors, all right, from the null space, okay? And I always suggest, even if you are very confident that you understand from where this come, when you write them down, take 1 second and verify that they are actually solutions to the null space problem, right? I mean, take this R, multiply with any of this S, and see that you did not miss any signs or anything like that. It's good to do a verification. All right. So we already said the null space has dimensionality n minus R, all right? So this is how many spatial solutions we have. Okay? Now, let me ask you the following thing, okay? So this particular problem with this R that we had here, all right, so let me put the R up. We have 3 free variables, 1, 2, and 3. Can you tell me, looking at these 3 vectors and the technique that I told you to derive them, convince me that these 3 vectors are independent of each other? Convince me by looking at them and saying, ah, that part tells me immediately they are independent. And I ask you what that part is. Look carefully at these three vectors and tell me why they scream at you and they say we're independent. There is something there that tells you that they are independent. What that something is? I have three free variables. What is that something that comes in that structure that you see that tells you that these are independent? Remember, linear independent means if you take combinations of the three equal to 0, the only way you can get that equal to 0 is if the coefficients are 0. So how about if I go a little bit further? The identity matrix is built in there, right? You have here, and the identity matrix is built around the variables 2, 3, and 5. You remember we take 1, we set it equal to 1, the rest equal to 0. We take the variable 3, we set it equal to 1, the rest equal to 0. Take 5, 1, the rest equal to 0. So the fact that we have that identity matrix makes this independent. Okay? So there's no miracle, there's no assumptions, there's nothing else here. It's that identity matrix built in the way we define the free variables that makes them independent. All right. Now let me go to a subspace we have not seen before. All right, that's the left null space. And we said the left null space gives us combinations of the rows, all right, that are 0. So we basically we're asking what are the dependencies between the rows that give me 0, okay? And obviously we look for non-zero dependency. So I'm looking basically for the vector y, so that when I multiply from the left, right, with R, okay, I get a 0 row vector. And remind you again, y transpose R is a linear combination of rows. So if you look at my R matrix, has the row 1, 3, 5, 0, 7, 0, 0, 0, 1, 2, 0, 0, 0, 0. So basically, I have to take y is a vector with 3 components. So I have to take y1 times the first row, y2 times the second, y3 times the third, and this is equal to the 0 row vector. Look at this and tell me what's the solution to this null space problem immediately. What non-zero y vectors can you get that basically satisfy this combination of the rows to be equal to 0? Look at that, when you sum all of this equal to 0, what is the solution for y1, y2, y3? What is the solution for y1, y2, y3? And again, you know what? The identity matrix which tells you what comes out as 0 and what is independent. And I already see an identity matrix there. Can you see it? Because of the pivot columns 1, 0, 0, 1. So when you sum all of these 3 to 0, what is y1 and y2 all the time? I mean, take component 1. If I take a linear combination y1 times 1, this is 0 and this is 0 equal to 0, y1 has to be equal to what? 0. Similarly, take component 4, y2 equal to 0. The only thing that doesn't have to be 0 is what? Say it again? y3. And it makes sense, right? Because you remember the third row, it was the row that we eliminated. It was the row that we eliminated because it was a combination of other previous rows. So obviously I can put anything for y3, all right? And that will give me a non-zero solution to the left null space problem. Okay? So what is the solution to the left null space problem if you want the base? Will be y1 equal to 0, y2 equal to 0, and y3 equal to 1. That's it. If you multiply that vector with any constant, it will also be on the left null space. So effectively, the idea here is these y's from 1 to r have to be equal to 0, all right? because they correspond to independent rows. And then everything from r plus 1 to ym has to be equal to 0, because that's how many 0 rows I have, right? That's how many 0 rows I have when I do the elimination. So the dimension basically of the left null space is m minus r. And it's easy to remember. What is m minus r? Is how many 0 rows do I have when I finish the elimination. That's the dimensionality of the left null space. OK. I'm going to give you actually a way. You remember, so let me give you a way to actually, in a general problem, compute the solution to the left null space problem. Pay attention, because there is only one slide, and this tells you everything you need to know in one slide. So in general, how do you compute the solution to the left null space problem? When you have, you want to find independent, y's that satisfy the left null space equation. So do the following. Here is the trick, and we will see why it works. Take the A matrix as we have it, and put next to it the identity matrix m by n, and do elimination on this combined matrix of A and I. So effectively, you're going to be multiplying both of this with elementary matrices. A is going to become R, and the identity matrix is going to become the product of the elimination matrices C. We agree? There's nothing fancy I have done now, OK? So I took A, put next to it I multiply this with the elimination matrices. Before, we only worked on A to get R. Now we have A and I. And obviously, this, when you multiply I with the elimination matrix, this is going to be E. And E times A is going to be equal to R. We agree? E times A is going to be equal to R. We multiply with the elimination matrices. That's how we do elimination, from the left. OK? So let me take one particular example of this. E times A equal to R. And let's say this is my A matrix, all right? This particular example. And my elimination matrix is going to look like that. So I multiply the elimination matrix with A, and I get R. OK. I want you now to look at this equation and tell me what combinations of the rows, what non-zero combinations of the rows I can take. Look at this equation and tell me what linear combination of the rows of A I can take to get the 0 row. I mean, before I gave you the answer, with on how we go to this 0 vector, but I want you to tell me looking at this elimination matrix C, can you tell me immediately what combinations of the rows of this matrix A have to take to get to this 0 vector on the bottom? What part of the elimination matrix tells me what combination of the rows of this matrix I need to take to get the 0 vector, the 0 row vector? Where is that information hidden? You remember when you multiply a matrix from the left with A, you can think of this matrix as 3 different rows, right? And the product of every row with a matrix is a linear combination of the rows. So concentrate on the product of the 3rd row times the matrix A. That will give you a linear combination of the 3 rows of A. And that linear combination has to be equal to what? So what is the linear combination of the 3 rows of A that you need to take? What is the linear combination of rows 1, 2, and 3 that you have to take? -1 the first row, 0 the second, and 1 the third. And you can actually see this because the first row and the third row are the same. Can you see that? Basically, conclusion. When you do elimination, if you keep track of the elimination matrix, okay, the rows in the elimination matrix that actually lead to zeros in the row reduced echelon matrix R are basically the basis of the left null space. They tell you what combinations of the rows you need to take to get to zeros, okay, in R. Everybody sees that? Nope. You remember why I told you early on in the course that we need to see things, products, as operations between rows and columns and all of these things. Here, if you multiply this row, minus 1, 0, 1, with this matrix, you take minus 1, the first row of the matrix, 0, the second row, and 1, the third row, to get the row 0, 0, 0, 0. All right? That's the definition of our left null space problem. So obviously, a solution to the left null space problem is minus 1, 0, and 1. A fantastic way to actually come up with a solution to the left null space. And if it happens here that we have, let's say, 3 0 rows or 5 0 rows, basically the corresponding rows in the elimination matrix will be the independent, you know, they will basically give you a basis for the left null space problem. Okay? All right. So done with that. I remind you once more, we already emphasized it, the column space of A is not the same as the column space of R. Never forget about this. Columns are being affected, but the pivot, the number of the pivot columns and the location of the pivot columns is the same for both A and R. So you can come up with a basis for the column space of A by looking, for example, in this case, can you tell me what's the basis of A looking at this picture once more? What is the basis for the column space of A? Thank you. That's it. All right. Now, the most wonderful picture that is all about, if you understand this picture, you understand everything about linear algebra, and only Professor Strang can come up, you know, with a schematic, basically, that so graphically tells you everything about linear algebra, about the fundamental theorems, actually, of linear algebra. Okay, we cannot discuss everything on this picture, but if you understand this picture, you're in business, because you understand linear algebra. So, let's look at the null space. The null space is the solution of Ax equal to 0. Its dimensionality n minus r, and it is a subspace of what space? The null space is a subspace of what space? Rn. You remember Ax, the matrix is Mn, so it's of Rn, okay? Where is Rn written? Oh, there it is, Rn. Now, obviously, so the null space, right, defines me a subspace of Rn, but also, do you agree that the row space is also a subspace of Rn? Because every row, it's vectors of with n components, right? So the row space is also a subspace of Rn, and what's the dimensionality of the row space? Is R, the rank of the matrix. And you notice R plus n minus R is equal to n. So basically, the row space and the null space, when you add their dimensionality, what do they give you? They give you the dimensionality of the space from where they come. And the dimensionality of the space they come is Rn, which is n-dimensional. All right. There is a lot of this in this picture. Let me ask you some trivial questions. Yep. You're ahead of me, and we are going to be coming to that. That's where I was going to go. And I was going to ask your imagination why the picture looks the way it does. Okay? So let me ask two questions. Why these two subspaces seem to be meeting there? Because this is a question I can ask in an exam. What is that point there? For something to be a subspace, right, of a vector space Rn, let's say, it has to be such that linear combinations are in the subspace. But say something, what did you say? The zero element. If they don't share the zero element, they're not subspaces. So both of these, they share the 0 element. All right? They share the 0 element. And then someone will, in response to what the comment we just heard, is why this, the way that Professor Strang plotted this, why this angle looks to me visually to be 90 degrees. What does that mean? Is that a coincidence, you think? So they are both subspaces of Rn, but as we will see in a forthcoming lecture, they are what subspaces? Orthogonal. So if you take one vector in this space and one vector in that space, and you take the inner product, it's going to come to be 0. And if they're orthogonal, together, they make the whole of Rn. Okay? The same thing. The column space is a subspace of Rm, has dimensionality R, and then the left null space has dimensionality M minus R. Obviously, again, they meet at 0, and they are orthogonal. And this is what you see there. If you include the orthogonality, you get basically the two fundamental theorems that define linear algebra. We're done. There's nothing else. All right? The rest basically come from this amazing picture that defines these 4 subspaces. And in principle, there is no way you can understand things you want to ask yourselves about solving AX equal to B unless you understand this picture. So this is not sort of abstract mathematics. It is really everything you need to know about linear algebra. And actually, with some imagination, if you are interested in mathematics, you can figure out that this type of ideas of subspaces and orthogonality and spanning the whole space, you can actually apply these ideas to functions as well, all right? But that's a subject that is a generalization of linear algebra that I will advise those who are serious about learning things to look further after this course. All right. So don't need any of these things. We already discussed. You don't have time to read, okay, or say anything. So, all right. So this is the dimensionality we discussed, right? So that, when you take the null space, right, and the rank together, the row space, or this is also the dimension of the column space, together they give you n. And so, I mean, that again that's the statement that I said a few times already. And you can do the same thing with the left null space, R plus M minus R equal to M. Okay. So let me, there's no way I can I wanted to do one very nice example, so we'll continue this on Friday, but let me do some trivial examples. Let me take the matrix A equal to 1, 2, 2, 3, so it's like a row vector. So we agree that M is equal to 1 and N equal to 3, right? What's the rank of that matrix? It says there. Do you agree that the rank is 1? You don't really have to do anything, right? Okay, so the rank is equal to 1. So the row space is a line. Actually, let me get rid of this. So the row space, okay, is dimensionality 1. Can somebody tell me the null space? What is the dimensionality of the null space in this problem? I mean, if you were going to do elimination, right, this will be your pivot element. So how many free variables you have? How many? 2. And you can visualize, right, if you take AX equal to 0, what type of geometrical object you get? AX equal to 0 will be x1 plus 2x2 plus 3x3. You will get a what? Equal to 0. What's that? What object do you get if you take x1 plus 2x2 plus 3x3 equal to 0? Is that a line? What is it? It's a plane. And what's the dimensionality of the plane? 2, right? You told me 2 spatial vectors that will define that plane. So immediately, can you see actually that the null space has dimensionality 3 minus 1 equal to 2, right? So 1 plus 2 equal to 3, they match very nicely. So let me actually get rid of this. Can you tell me how many independent columns you have? 1, all right. And what is the dimensionality of the left null space here? Remember, the left null space is you multiply on the left with a vector y, right? In this case, because y is, A is a raw vector, that will be a scalar. So what is the dimension of the left null space? 0. And you expect this because what's the dimensionality of the left null space? Is m minus r. What is m? Equal to 1. R is equal to 1. So 1 minus 1 gives you 0. Yep. It says that in the computer in the notes too. It does? OK, so refresh the screen because sometimes you read things that they're out of date. I change them as I speak. OK? All right. So let's do another example. This problem is we have m equal to 2, n equal to 3. And it says the rank is equal to 1. By the way, why is that? Can you just, so we don't have time to do everything here, why the rank is equal to 1? And somebody can give me a reason immediately? The two rows are basically multiples of each other. OK, so the rank is equal to 1. So how many free variables in this problem? What's the dimensionality of the null space? What's the dimensionality of the null space? 2. And actually, you know what? If you know that the r is equal to 1 and you have n equal to 3, the dimensionality of the null space is n minus r, which is 2. OK? What is, how many independent columns I have in this problem? R is equal to 1. So how many independent columns? 1, right? Because you can see 2, 4 is 2 times this, and 3, 6 is 3 times that. So what's the dimensionality of the left null space? Remember, the dimensionality of the left null space is m minus r. So m is equal to how much? 2 minus 1, so it is 1. OK? All right? And if somebody asks you to write down the basis, etc., I think that information may be contained already in the slides. OK. All right. I have actually 3 minutes. I can start this problem because there is sort of linear algebra, actually. If you play the correct game and you compute the subspaces, you can see that any problem in engineering and the sciences can be written down simply with linear algebra calculations. Every problem. So every problem in electrical engineering, if you have circuits, in structures, in hydraulics, I don't know what your background is, if you do any problem with finite elements, whatever, somehow there is some unified form that comes up, and that unified form, I would like to introduce it by doing an applications of linear algebra, the things we learn, to problems that are defined over graphs, all right? And use your imagination and think of these graphs being circuits, basically, from your undergraduate course. So what I'm going to do is, and I'm going to only tell you what the problem definition here is. We're going to assume that we have this graph with nodes x1, x2, x3, x4. And then we're going to have these variables that you can think of this. So you can think of x's as currents, as voltages in an electric circuit. And you can think of these y's as currents that go in some directions that the way I saw them, I have defined them to be positive. Okay? So you can think, again, x's to be the voltages and y's to be the currents. Okay? And so the matrix A that I'm going to play with is a matrix that we have seen before. Can somebody tell me what name we use for a matrix like this? Maybe in lecture 1 or lecture 2, we call a matrix like that something. What does this matrix do? I notice here x2 minus x1, x3 minus x1, x3 minus x2, x4 minus x2, x4 minus x3. What does this matrix do? So we call it a difference matrix, okay? So you can actually think what this matrix does, right? It gives me the difference of the potentials between two nodes. And for those who remember something from electrical engineering, the difference in the potentials through Ohm's law is related with the current in that edge, all right? So A times X gives me the difference in the potentials. Okay. So, so this is my matrix A. The matrix A, if you look at the columns, corresponds to the 4 nodes, 1, 2, 3, 4. And if you look at the rows, each of the rows corresponds to the edges of the circuit, but in this particular case, there are 5, okay? So do me a favor, so you can allow me to actually move to something else, you know, on Friday. Take a look at the remaining of the slides, and I want you basically to see how everything you learned in circuits, it is manipulation of the fundamental subspaces that we learned up to now, and actually the structure of the final equations that you get looks like the same sort of equations you get in every numerical method in engineering and the sciences. And that is not a coincidence. So somewhere we will see that the matrix A transpose A is going to come to play a role. Not just A transpose A. Anybody, does A transpose A resonates to anything that you already know? If you have matrices and somehow suddenly A transpose A comes, does it remind you anything at all? Projection, right? Something, another word? A transpose A, where is that coming? Best fit, least squares, all right? So optimization problems where we try to find the nearest solution, all right? And so we will say that somehow linear algebra and playing with the fundamental subspaces tell us all of this and much more, okay? So we'll do this on Friday, continue this example, but look at the slides, and I'm going to download also a video lecture 9 that talks about basis, elementary things, but read it because they are needed. And of course, there's going to be a homework. It's already posted. And I'm going to email, hoping that this time I'm more lucky with the next 7 people that I'm asking to prepare a LaTeX solution. And when I ask for a LaTeX solution, I don't ask for one to arrive the day the homework is due. All right? Because by then, guess what? I have already typed the whole solution myself. Okay? Because life is short. Okay? We need to keep moving. So keep that in mind. All right, so see you Friday.